Okay, so also I think you have noticed I have increased the deadline for homework 2 up to Thursday. That is 30th of September. But please don't copy others' solution. I will be very strict on that. I have increased the time so that you can do yourself. Whatever, how much you can do yourself, you can submit, no problem. That will help you in the final exam. But my suggestion is not to copy others' solutions. That will not help at all. Okay, that is one thing. And the second thing, those who have missed a class test for some reason and you have mailed me earlier, just forward those mails to me as early as possible. Okay, I will give one makeup only for those who have mailed me earlier. Not anybody, anybody's exam will be counted, but those who have mailed me earlier with proper reason, just forward that mail to me so that I can identify who has valid reason to miss a class test, and then I will take one makeup for only those students. Okay, so please forward those mails. You have mailed me earlier anywhere in the trimester. Okay, so then let us go back to our class. So last time, I think last class we have covered the introduction part of data link layer, and then we say data link layer has two parts. One works in the software along with the network layer, and the other part works with the hardware with physical layer. And we have also covered what are the different services provided by data link layer. Now the next section we will start today is multiple access links or protocols. You can see different pictures in this slide. The first one, shared wire, cabled Ethernet, where one cable is shared by multiple nodes. If we use hub now, actually the idea is same. Also, we use cellular or mobile network, 3G, 4G, or 5G, where there is a base station and there are multiple nodes. They are communicating again using the same shared channel, shared radio. Another example is Wi-Fi. Many of us actually use Wi-Fi. Wi-Fi is very common now, but in Wi-Fi, in fact, there is one single channel shared by all. So there are 11 possible channels, we can say, but one channel at a time that is used by all the nodes. So basically at a particular time, only one communication takes place. Although using Wi-Fi, we can connect many devices, many communications can be done, but exactly one channel is used at a time. So that is shared by the devices. Then satellite, similar idea, but there are different transmitter and different receiver. Receivers are on the earth and the transmitter on the orbit. And then receivers receive signals from the transmitter. Multiple receiver can receive the same signal. So again, shared media, air or vacuum as the shared media. And then finally, there is a real life example of human party program, or even you can consider our class. We had physical classes, and now we are having online classes. Again, I am talking and then you are listening, but anybody can unmute himself or herself and then talk. But if multiple students talk simultaneously, then there will be what we call interference, noise, and in networking term that is collision. So if that signal collides, if there are lots of noise, lots of interference, then actually we cannot hear, we cannot understand. So that is also true in a physical gathering. If there are smaller groups talking to each other with different level of power, different level of voice, still communication can be done with the presence of noise. But if there is too much noise, then we cannot hear. So there is no communication. So this is a good example of multiple access, where multiple nodes will communicate simultaneously. Now, in different situations, the protocol must deal with differently, but these are commonly called multiple access links or protocols. And the responsibility is handled by data link layer. And there are basically two types of links. One is called point to point. You can understand what is point to point. Suppose two routers are interconnected, two PCs are directly connected, and point to point protocol for dial up, or for maybe for BTCL connectivity, DSL connection, internet connectivity. So point to point means there are two nodes connected to one cable, so no possibility of collision or interference, right? One transmits, another one receives. One other example, good example of point to point, is when you connect a host with a switch. Okay, you connect a host with a switch port, so that is point to point. There is no possibility of any collision. And there is second category that is called broadcast, where shared wire or media used by many devices, like the earlier in Ethernet, and also the hybrid fiber coaxial. We know the dish cable, dish connectivity, where we get TV, cable TV, but through the cable TV we can also provide the data connectivity. So that is another example. And then Wi-Fi is a very good example. Cellular mobile network 4G, 5G is a very good example of shared broadcast media. So these two categories, any protocol will be maybe point to point or broadcast. But we will mainly talk with the broadcast multiple access links. So in that case, there is a single shared broadcast channel. And since the channel is shared, if more than one node simultaneously broadcasts or transmits, then what is happened is interference or noise, and we call that a collision. So if more than two nodes transmit simultaneously, some data will be actually damaged, and then we call it collision. If two or more signals a node receives at the same time, or if a wired media, one signal is superimposed by another one, then no signal we can receive, so that is called garbage, and then the entire frame, entire packet is damaged. So what the multiple access protocol should do, it's a distributed algorithm that determines how nodes share channel. That means how we can overcome, we can avoid collision interference, or even if we accept collision or interference, how we can overcome that. Determine when a node can transmit so that no collision will happen, or we can successfully transmit that thing. So that is the main idea of multiple access protocol. And another important thing about all the protocols in networking or communication is we want to transmit the real data, real message. But to transmit that, we have to transmit some we can do some coordination, send some coordination messages, like the headers, like special messages we'll see. But all those messages must use the same bandwidth, same capacity. So it's some kind of overhead. There is no out of band channel for coordination, so that our capacity of the main link will be utilized 100%. So if there is a clear trade-off. If you add coordination among the nodes, so no collision will happen. But then for that coordination, you have to use up some of the bandwidth, right? And if you want to just remove the coordination so that overhead will not be there, then what can happen? Collision can happen. You cannot avoid. So there is a trade-off. And now some protocols avoid collision, some protocol allow collision and then recovers from collision. So this is about multiple access protocols. Now, if we categorize all multiple access control protocols in data link layer, we can divide them into three broad classes. Okay, first one I think we have seen in chapter 1 when we read circuit switching. If you remember, frequency division multiplexing, and then time division multiplexing, code division multiplexing. The idea is divide the entire channel into a smaller pieces in terms of time, in terms of frequency, in terms of code. And those pieces are called slots, okay, in terms of frequency or code or time. And each slot is exclusively given to a user for use. Even if the user is idle for some time, but the connection is there, nobody can share that particular piece. So that is the idea of channel partitioning. We already know the advantage is there will be no collision, right? There will be no interference because each one is using separately. In mobile, when we talk, when we connect, we get a channel exclusively for use. So there is no sharing of that channel. So that's why no collision. But the problem is it will have less utilization. If user use 20% of the time actively, then 80% of the time it will be idle, but nobody can use. I think we saw it in chapter 1. So this type of protocols has these characteristics, advantage and disadvantage. Second category is random access. Random, you know, random. Random means anybody can talk anytime. In the class, anybody can ask me any questions. Even if I am talking, then you can ask. But normally what happens, before you ask, you try to find a time where I stop, right? So if that happens, then collision will not be there. But that is practically, most of the cases, not possible. So in random access, anybody can transmit data anytime, whenever it has data. And then what is inevitable must be there? Collision, right? Collision will happen. And then this type of algorithm must tackle these collisions. That means how to recover from collision. What is meant by recover from collision? We have to successfully send that packet or frame at a particular finite time. If we fail to send previous 2 times, in the 3rd time maybe we are successful. That is called recover from collisions. We'll see one example later. And third and final category is taking turns. This is very common. I think boys, you have played cricket. Those who love to play cricket, we have faced somewhere, sometime, that using numbering, right? So who will bat first, who will ball first, use the numbering. So there is no collision, no confusion. 2 wants to bat first or 5 wants to bat first. No, we will do numbering 1, 2, 3, 4, 5. Then if you are number 3, you will do at number 3. So that is the idea of taking turns. When you turn, you transmit. When the others turn, transmit. Still no collision because I am numbering, I am fixing the turns. But again, this type of protocol must need some kind of coordination by some coordination node. So again, delay is a big concern here. Overhead is a big concern here. And interestingly, you will find that random access gives the best result in local area networks, but there can be collision, but still the utilization is high. Okay, we will see some examples here. So TDMA, FDMA, I think we have mentioned in chapter 1. So you know that in TDMA, time is divided by different slots, and a number of slots is divided into frames. So suppose 1, 3, 4, there are 3 stations, 3 devices. They will be given 1 slot per frame. So it will be repeated one by one. No possibility of collision. But you can see 1, 2, or 3 slots are free. Or if one doesn't transmit all the time, still someone else cannot share. Okay, so that is the problem of utilization in channel partitioning. Similarly, FDMA, frequency will be divided, the same thing. Okay, we have covered in chapter 1, but we are in this chapter we are more concerned about the random access protocol. You know Ethernet. Have anybody heard Ethernet so far? Anybody? Did you hear Ethernet, the keyword? Adrita? Mehdi, Enamul? Did you hear Ethernet? What is
Yes,
Ethernet?
Ethernet is the port we use to connect to our PC or our laptops.
Right, that is wired LAN. Ethernet is a protocol used for wired LAN, and Ethernet uses random access. And random access performance is best among all the protocols. Okay, so what is the idea of random access protocol? When a node has packet to send or data to send, it will transmit. And when a node transmits, there is no piece, no division of channel. Okay, the entire capacity will be used by that packet. If capacities are interconnected, I think in chapter 1 we have mentioned that L by R. If you remember, L number of bits, R is the capacity, so the time is L by R. So the packet will use the entire capacity. And there is no a priori coordination among the nodes. No coordination. So that's why it is efficient. But what is inevitable? There is no coordination. So it can happen. Multiple nodes can transmit simultaneously. And in that case, we have to face collision. Collision means two signals collide. And if you think about a packet, a frame, for example, Ethernet frame, that is 1500 bytes. So 1500 bytes means 1500 into 8 bits, right? So each bit will be converted to signals, we know. So if we need to transmit that 1500 bytes, when a node starts transmission, it must end the entire transmission. It is not like I have transmitted 100 bytes. So, okay, rest 1400 bytes I will transmit later. No. Whenever a node starts transmitting a single frame or packet of 1500 bytes, it must be finished. If by this time any other node, any other signal collides, the entire frame of 1500 bytes will be wasted. Not only those bytes, those collided. The entire frame, entire packet will be damaged. So what is the consequence? We have to retransmit the entire frame again. You got my point? So that is the idea of collision in random access, and we cannot actually prevent collision in random access because there is no coordination. So that is the problem. So whatever protocol, random access protocol we use, must deal with two things. Keep in mind two things. One is how to detect collisions. Now in wired network, how to detect collisions? In wired network, you connect a wire to the port of LAN card, right? NIC card, network interface card. And then if you just connect, the hardware can measure the signal it is transmitting and the signal it is receiving in that port for where that is possible. So if the two signals are different, that means what? That means collision, right? So collision detection easy in wired LAN, but in case of wireless, we'll talk later. In case of wireless, it's a bit complex. Collision detection is not that easy, but any random access protocol must detect collisions. And secondly, not only detect collisions, we have to successfully transmit the frame, right? So then it must also specify how to recover from collisions via delayed retransmission. So we must retransmission sometime later. So these two things must be handled by any random access NAC protocol. Okay? Anybody has any question up to this point? And some of the examples of random access protocols: Aloha, slotted Aloha, CSMA, CSMA-CT, CSMA-CA. I think you have read some of these in data communication or communication theory or digital communication, right? Yes or no? Did you see this, any of these protocols in any of the earlier courses? No? Nuzhat?
No, sir.
No. Okay, no problem. Actually, we will try to cover one. Yes, there are some primitive protocols. Aloha is very primitive, not used. And then CSMA. These are the actually sequence of protocols. And CSMA-CD used in wired LAN, CSMA-CA used in wireless LAN. But the idea, let me give some idea. What is CSMA? Since if more than one node transmits, there will be collision. If there are more number of collisions, your performance will be worse. So we want to, also there is no coordination. So we cannot like prevent the collision. But we can modify the algorithm in such a way so that the collision will be less. Probability of collision will be less. How? One thing is that is maintained by normal CSMA, simple CSMA, that is carrier sense, multiple access. So carrier sense means sense your carrier before transmit. So if a node needs to transmit, it has data to transmit, it first check the channel. If the channel is idle, only when it starts transmission. But whenever it starts transmission, it must complete transmission, the entire frame. Okay, that's why there is a possibility of collision still, because the frame size is large. So the entire time we must make sure no other device starts transmission. In that case, it will be successful. But if the channel is busy, that means someone else is transmitting, then defer transmission. Then the node will not transmit, it will wait for some time. Okay, so that is the idea. But as I said, still collision can happen. Still collision can happen. So what CSMA CD does, it adds a new mechanism called collision detection. As I said, collision detection is easy in wired LAN, but it is difficult in wireless. So that's why wireless networks don't use CSMA CD, they use CSMA CA for collision avoidance. That is actually in chapter 7 of our textbook, but we will not cover that chapter. But you can get the idea. CSMA CD can be used in wired LAN only. And in wired LAN, whenever a collision is detected by the hardware, it will stop the transmission right away. If the data is 1500 bytes and it had transmitted 100 bytes and then collision detected, it will not transmit the rest 1400 bytes, because that will be just wastage. Okay, so abort the transmission and then implement the mechanism how to recover. That means wait for some time and then retransmit at a later. Okay, it's a analogy is the polite conversationalist. Okay, that means it will see, okay, if someone is like I am talking, then you will stop. You are talking, then I will stop. So CSMA CD is like this. Okay, and then the third category, taking turns, we will see two examples, although these are obsolete now. But the idea is, one is polling. There is a master node that invites other to transmit in turn, but in turn. So master node will say, okay, now it is your turn, transmit data. Now it is your turn, transmit data. Typically used with dumb devices. And concerns means the drawbacks in this type. First one is overhead. Definitely someone needs to coordinate, so that means some overhead will be there. Delay will be more, okay, because waiting time will be more. And then single point of failure. If the master node fails, the entire mechanism fails. Okay, so that is the idea of polling. Then the second one, like this, polling is like this. So master node will tell some node that, okay, it is your turn now, send data, like this. Okay, and the second example is token passing. So there is a box called token that carries data, and it just moves clockwise or anti-clockwise. Okay, like this. And then if a node has nothing to send, it will just forward the token. No, I don't have any data. Then if some node has data, it will add the data to the token, and then the token will be forwarded. Again, overhead is the problem, delay is the problem, and single point of failure is the problem. If token doesn't work, then the entire mechanism will not work. Clear, everybody? So we have seen some idea and examples of different classes of MAC protocols. Any question? Okay, no question. Then let us move. Okay, next important concept is a protocol called Address Resolution Protocol, ARP. It is a very, very important protocol in networking, and very, very important also for in the security perspective. So first we need to know why we need ARP. And to understand that, we need to understand a question. I will ask you a question, keep in mind. And before the question, let's just review. We have covered IP address. We know IP version 4 has 32 bits. And also we have covered MAC address, physical address. that is the address usually used locally to get frame from one interface to another physically connected interface in the same subnet, and they are physically connected to each other. So in that case, we use MAC address, right? Because that is used by data link layer, because every link has two devices in two sides. So when we change one link to another link through router, then definitely the MAC addresses will change. And also we know the MAC address is 48 bits, and it is burned in the network interface card ROM. What is network interface card? Anybody? NIC. What is NIC?
It's a LAN card.
Very good. LAN card. Actually, LAN card, network interface card, same. So when you buy a LAN card, or a LAN card is built in your motherboard of laptop or PC, that LAN card has a built-in MAC address, 48 bit. So normally MAC address is, that's why it is called physical. So it's fixed. Although we can change sometimes using software, we can set a new value, but that is in software. In hardware, value is there always. Now,
But sir, we can clone MAC address.
sorry.
So we can clone MAC address.
Right. We can clone. But that is software settable, not settable in the hardware. Hardware MAC address is fixed. That is not like you changed a MAC address for using software. Then that will be used in the system, but the hardware MAC address will be there, the original one. Okay. So we know MAC address, we know IP address. Now the next question, IP address, MAC address is represented hexadecimal, we know. And if you consider a scenario, a simple scenario shown here, 4 hosts are interconnected, each one has an IP and each one has MAC address. Now, if I ask you, when the communication starts, or how as a user I can initiate a communication, when we give facebook.com, right? When we give google.com, or if I know the destination IP address, when I give the destination IP address. Correct? Without giving the IP address of the destination, communication can never start. Remember. So if you give facebook.com, actually facebook.com is converted to an IP address by DNS. We know that. So basically, if you consider now this simple network where 4 PCs are interconnected, if I want to communicate from 137.196.7.23 to the 137.196.7.14, can anybody tell me how I can communicate? Suppose the networking configuration is 100% correct. All the things have been done. Now I want to access 7.14 PC from 7.23 PC. How I can do that? Anybody? Show me. Can you tell me? Suppose you have set up a network of 4 hosts. Now you want to communicate from one host to another host. How I can do that? Any idea? We are doing that every day.
So through IP address.
Sir, IP address.
Very good. Nuzhat and Adrit, both correct. Through IP address. We must give the destination IP. Otherwise, we cannot communicate, right? Okay, show me. So if you have the destination IP known, you can communicate. I think you have used server 16 when we had physical classes at UIU, right? You cannot access from home, but you can access from UIU labs, UIU network to that server 16. Can you remember 10.100.100.16?
Yes, sir.
Okay.
Yes,
How can you access? You have to give this IP address through run, right? Through Windows run, or through the any software interface, or through the browser. You have to access, right? But in any case, you have to give the IP address of the server. So what I'm trying to say, when we communicate, we give the IP address of the destination. Now we are at the data link layer. We know one thing. Even if I give the IP address of the destination, IP address works at the software. So to transfer the data or packet or frame by converting to signals, the node needs to know the MAC address of the destination, right? Because without MAC address, a frame cannot be created. Because hardware frame must need the hardware address of the source and the hardware address of the destination. But as a user, we never give the MAC address of the destination. So if 7.23 now wants to communicate to 7.14, it knows the destination IP, but how can it know the MAC address of the destination? You got my question? Did you understand the question? The question is, again, the question is, if we know, because as a user, we give the IP address of the destination. If we know the IP address of the destination, still we need to know the MAC address of the next available device. The next device connected with the link, so that we can transfer the frame even before transmitting the frame as signals. We need source MAC and destination MAC in the frame header, right? So knowing the IP address, how can we know the MAC address? Is the question clear? Yes or no?
Yes, sir.
Nuzhat, clear? Mehdi?
Yes, sir.
Okay. Then if the question is clear, then the answer will be simple. The answer is ARP, Address Resolution Protocol. So the question again here, how to determine destination MAC address if I know the destination IP address? That is the question basically. Because IP address is given by the user, so the PC knows the destination IP. But how the PC knows the destination MAC? This is automatically done by ARP. And if you connect a device to the network, ARP is automatically done. I can show you. If I go to command prompt, you can also do that with me in your PC. Just give a, can I increase the, oh no, font size. I cannot, sorry, I cannot increase the font size. Okay, so just I'm telling you, ARP-A. You can use your command prompt and you can give this command ARP. Yes.
Properties কি font size change করা যাবে, right click করে।
Oh, okay, but okay. Properties. What is the properties?
স্যার মানে command prompt white screen এ click করে right click করলে।
Okay. Let me just you don't need to see all the values. Just need to get the idea. If you put a command ARP-A, then you will get a table, and in the table, if you can notice, there are on the left side there are IP addresses. Okay, there are you don't need to know every IP address, but there are IP addresses and there are corresponding MAC addresses in this table. So this is basically an IP to MAC address mapping. So that's what I am trying to say. ARP we don't need to configure. Whenever a PC, a device is connected to the network, ARP automatically works. And anytime if I want to see the table, I can give the command ARP-A. But basically, what we see is this ARP table. And in the ARP table, each reachable IP address with their corresponding MAC address is shown in the ARP table. And initially, if the ARP table is empty, suppose a node is connected right now or a PC is restarted, shut down. So when ARP table is empty, then the protocol works to get the MAC address of every possible IP address in that particular segment. And each entry has this part, IP address, then MAC address, and then there is a TTL. TTL is time to live, how much time it will store. It will be stored in the memory. It is typically 20 minutes. That means within 20 minutes, if no communication is done to that particular PC, then that is again removed. Okay. So this table is maintained by every host. Why? We need to understand, for the framing, a node takes a packet at the source or sender, takes a packet from network layer, adds frame header. In the frame header, we need source MAC and destination MAC. Source MAC is known because this is the host MAC, but the destination MAC, if known, if ARP table is filled up, known, But if ARP table is not filled up, then it must follow a protocol that we call ARP. How that works? Let us see an example. Suppose A wants to send datagram to B and assume that B's MAC address is not in A's ARP table. For example, ARP table is now empty. How A will know the MAC address of B? Because without B's MAC address, A cannot create a data frame. Okay, so what A will do? See, A's ARP table is now assumed empty. We want to see how ARP protocol works. So what A will do? Step 1, A will broadcast, because A doesn't know who actually is B. So A will broadcast an ARP query contains B's IP address, because B's IP address is known. As a user, I have given B's IP address, so A knows B's IP address. But A needs B's MAC address. That is not there. So it will broadcast in a special ARP query message. See, this is not data. This is not real data frame. This is just ARP message. It will contain a destination MAC address, all F. This is a layer 2 broadcast address. You know, in layer 3 IP address, all host bit 1, right? IP address broadcast. In case of layer 2 MAC address, if you give all binary 1, that is broadcast of layer 2. What that means? If a switch receives a frame with destination IP all 1 means in hexadecimal all F, right? Binary all 1 means hexadecimal all F. So if a switch receives a frame with destination MAC address all F, it will send to all. That is broadcast. That is the idea. Now every node C, B, and D will receive this broadcast message, but C and D will not process because their IP doesn't match, right? Only IP of B matches because that is given. Target IP address 7.14, you can see. So B can check, okay, this IP address matches with mine. So I have to send my MAC address to the reply, with the reply, okay? So what B will do? It will create a ARP response, ARP reply by giving its MAC address like this, okay? And then after receiving this in step 3, A will update its ARP table like this. Is it clear? Any question? Okay. If not clear, please tell me. So that means when A doesn't have any entry for B, destination MAC, A will run ARP protocol. It will send special message, ARP message. This is not data frame. After getting the MAC address of B, now A will create a data frame with source MAC, its own MAC, and destination MAC with B's MAC. And then that data frame will be sent to B physically by converting to signals. Okay? So in a single segment, how that works? Simple. But when there is router in the middle, B is in a different network, then what will happen? Or the question will be, should A need the MAC address of B in its ARP table? Yes or no? What do you think? Anybody? Any idea? In the previous case, all the nodes was in the same network, same segment. So all are physically reachable. No need of router. But now B or destination is in a different network. There is a router in the middle. So what do you think? In A's ARP table, will it store B's MAC address?
Yes, sir.
No,
Normally,
sir,
it
it
should.
will store router's MAC address.
Very good, Adrita. Very good. Because if it needs to know the B's MAC address in its ARP table, what happens when I browse Facebook, when I browse Google? They have thousands of servers. How can I know each MAC address, each server's MAC address, right? That is not feasible. So fortunately, we have a very, very nice concept of default gateway in networking. that makes our life easier. Doesn't matter destination is connected to this router R or destination is beyond 100 routers, doesn't matter. If destination is not within the network, then A will send the packet to whom? To the
So
router,
router.
right? To the router. So solution is simple. So never a node will need to know the MAC address beyond the network, beyond the segment. That makes easier, things easier. And that is because another reason why default gateway is so important. Now, how that will happen? Let us see another example. All nodes has corresponding IP address and MAC address. Now, again, A wants to send a datagram to B. But in this case, there is a router in the middle. So A knows B's MAC address. Again, when as a user, I have given B's IP address, not router's IP address. B's IP address as the destination. So A knows IP address of first of router also, because we have definitely configured default gateway. When you configure IP address subnet mask, I think in the lab you have also done that. So every node should have the default gateway address, that is the router's address. How? Because we need to configure that when we configure IP and subnet mask. But also A knows R's MAC address. If I assume A knows R's MAC address, how? Can you answer? How A knows R's interface's MAC address? Using ARP, right? Using address resolution protocol. Because router's interface is part of the same segment. So the same way, that's why routers LAN interface have MAC address. Each LAN interface has a separate MAC address, because that will work like a same host, right? Like a host. So in the same segment. So what will happen here? You can see, suppose A received a packet from the network layer, and its data link layer will add a frame. How? It will add a header. Now it needs the MAC source and MAC destination. So MAC source will be source of A, right? MAC of A, simple. But what will be the destination MAC? Will it be MAC of B or MAC of R? What do you think? Nushat, Mehdi, Anamul, I think Adrito, you
MAC of
understood.
A separate.
MAC of A is the source, but it needs the destination MAC, where A will forward the frame to R or to B directly.
To R.
Right. So that is the logic. So that's why A needs R's MAC address, not B's MAC address. And you can see the destination MAC, the red colored E6, E900. This is the MAC of router's interface, not the B's. Now, this frame will be sent by A physically to router. Can you remember, we have seen one animation in chapter 1 during lecture 1 or 2. You can go through again and you can see the same concept again here. But now we know the details of headers of different layers. So it will be more understandable. So router will receive this. Router's data link layer will remove the header. What we'll get? We get the packet. So router will decide based on the destination IP where to forward. And again, router will give its data link layer to add header to create a frame. Now the source MAC and destination MAC will change. We have also covered one example, example 12 in chapter 1. If you go back there, same thing, but now more details. So source MAC will be now router's right side interfaces MAC, and destination MAC will be now B's MAC, and that must be known to the router's interface because they are in the same segment using ARP. Clear? So now router will forward, router's data link layer will forward the frame to B. B will remove the header, and B will hand over the packet to the network layer. That is how it works. Is it clear, everybody? So there are two cases. One is no router involved, no default gateway. Another one is routers involved. Doesn't matter one router or 100 router, because the default gateway is one. Default gateway is the interface to which the host is connected. So even if we want to communicate with Facebook or Google, the idea is same. ARP will work only within the segment. Clear? Anybody has any
Sir,
question?
can you explain again how we can send data without default gateway?
Without.
Yes, sir.
Without means you must have a single network like the previous one. See? Here, single network. So what are the device in the middle? Maybe hub or maybe switch, right? But whenever you connect multiple network, you must have a router in the middle, one or more. So in that case, okay, in that case doesn't matter one router or 100 router. For A, the default gateway is one, to which this host is connected, right? So the idea is same. If you see one more time.
Sir, without default gateway, how computer will know that we are in same network?
Okay, that is actually part of IP addressing. Did you complete the networking lab? Are you in
Yes,
the
sir.
networking? So you have done subnetting, right? So
Yes, sir.
whenever we give a destination IP, the PC we are using has its own IP, right? Has its own subnet mask, right?
Yes, sir.
So it can get its own network part.
Oh,
It can get
yes, sir. I can remember, sir. First 24 bits are same.
not 24. No, that's about MAC address you are
Say-
talking about. But to know whether destination is in a different network, we need to compare the IP address. So the network part must be different. So if you apply the subnet mask to source IP and subnet mask to destination IP, you will get both the network part, right?
Yes, sir.
If those network parts are same, then we don't need default gateway. Is it correct?
Yes, sir.
If the network part is not same, definitely we need to hand over the packet to router. We cannot directly send to the different destination in that case. Is it clear, Adrito?
Yes, sir.
So that is the idea. See, we have to connect the main concept everywhere. Now we are the data link layer. You have to be clear about the layering concept to understand this. Especially I am telling this for all others. It's not a separate entity. Everything must be connected to the layering concept. So how a node knows destination is a different network, that must be there. It is using the destination IP and subnet mask. Okay. And then if it decides, okay, destination is in a different network, then it will forward the packet to router. That is defined already. That is the idea of default gateway. And in case of ARP, the same thing happens. Okay. Is it clear now? So just go through this every step, and also it is described in the textbook. So if you understand the process, you are done. There are only two cases in ARP. Okay. We have one more section left, but let us do it in the next class. We have a makeup class on Monday, and then we'll do some hands-on examples on Monday. And I think in the last class on Tuesday, we have more time to discuss about problems and the final exam syllabus. Okay. Anybody has any question? No? Okay, if not, then let me just stop presentation.
স্যার
Yes.
স্যার কাউন্সিলিং টাইম কি অন্য সময় দেওয়া যায় স্যার? ওই টাইমটা একটু ক্লাস থাকে, এই জন্য অনেক সময় দেখা যায় আসা হয় না।
In that case, you can come at 7:30. 7:30 every Saturday. Today I have a counseling hour for MSCSC class, but you can come to that time, no problem. Okay, today 7:30. And also you can email me if you need emergency. You can email me. I can give you some time. If I can solve through email, that's fine. If you need some 2 or 3 minutes, I can join. Okay, so you can email me. I can give you time of Zoom link, not the Google Meet link. and then you can join at that time. I can give you some time. Okay, that's on appointment, other than the regular schedule of counseling. Okay, then thank you.